Welcome. This is PHY 2048 laboratory, and this is a dry lab concerning the I'm calling it floating dowel. Sometimes it would be called the hydrostatics lab. So let's explain what's going on here. Let's begin our notes. This is a relatively brief lab. So this is lab, and I can't remember the number of it. And then this would be, let's call it floating dowel lab, maybe hydrostatics. There's just so many different hydrostatics labs you could do. Don't forget, you're going to put the date on here and you're going to put the page number in the corner. Remember, we're writing in a lab notebook, so we can be informal. So the objective, our objective is, well, let's have a look. What is our objective? Our objective is today we measure the density of a wooden dowel by analyzing its BOUY buoyant properties. We compare our result with accepted values for different kinds of wood. Cool. Let's have a look at our setup. And again, you can do a freehand sketch if you put the board around it with a ruler, because then you say, subconsciously you're saying to the viewer, oh, they had a ruler, but they like to do freehand sketches. Alternatively, you can just use a ruler for your drawing. It's like you get used to it. What we have, the important bit, is we have a dowel and we want it to float in water. And here's the catch. Typically, if you have a dowel and you have it floating in water, it will kind of lay on its side and you'll get something like that, which is very hard to work with. We'd like to have it so that the dowel would stand upright. And we'd have the meniscus of the water there, and we could compare how much of the dowel is above the water to how much of the dowel is below the water. The best way to do this is best way I can find anyway, is that we get a graduated cylinder. And we drop the dowel into it. Now the graduated cylinder has to be just bigger than the dowel, and the ones that we have in our laboratory are like that. And then there's a meniscus formed on each side. Let's not make it. Let's always try to avoid symmetry. When you're doing anything, try to avoid symmetry, because then you don't have a big and you have a little, you have two equal ones, and yet they're not the same thing. And let's call this L1 for the total height of the dowel. And then let's call this L2 for the amount of the dowel that's submerged. I'm not going to use the markings on the graduated cylinder. I'm going to use a ruler. So this is a graduated cylinder. This is wooden dowel, and that's kind of it. This is just, oh, this is water. We have to know the liquid. We have to know what the material is that the wooden dowel is floating in. Okay, let's do a bit of theory. Theory. And okay, the theory is going to be, let me see if I can remember this. Oh yeah, I remember that for floating, the buoyant, B-O-U-Y, buoyant force equals the weight. What happens is, here's my object. I have a buoyant force caused by the weight of displaced fluid. The buoyant force is all about the fluid, and this is going to equal, well, it's going to be the density of the fluid. That's going to be in kilograms per cubic meter times the gravitational field strength. Oh, I nearly said acceleration due to gravity. Sorry, no. Gravitational field strength. And that gives me a newtons per cubic meter. And then we have a volume of displaced fluid. So it's kilograms per cubic meter, which then becomes newtons per cubic meter, which then becomes newtons because I multiply by cubic meters. And down here we have the weight. Let's call it Fg for force due to gravity, and this equals weight of object, and this equals the density of the object, in this case the wood, times G, times the volume of the object. And what we know for this setup, because it's floating, these two are equal size. Okay, so let's play with this a bit. What I can say is that the density of the fluid times G times the volume of the displaced fluid, that's effectively the volume of the object under the surface of the water, is pushed the fluid out of the way, is equal to the density of the object times G times the volume of the object. Well, of course my G's cancel. This would also work just as well if you had a little space capsule on the moon, I guess, because the G's cancel. And then we have, well, we're trying to find the density of the object. So the density of the object is equal to, let's have a look, the density of the fluid moderated by the volume of the displaced fluid over the volume of the object. And actually, if you think about it, these two volumes, again, there's my meniscus, this is my L1, and this is my L2, and this here is my A. So I get the density of the object is equal to the density of the fluid times the volume of the displaced fluid. The volume of the displaced fluid is L2 times A over the volume of the object, which is L1 times A. And those two guys cancel. Oh, so if I measure the ratio of the two lengths, I'll get the ratio of the two densities. Okay, so then we need to be lab partners. So we need to get a data table. And it's good practice to number your data tables, because you'll be at a stage where you're doing reports and there'll be a whole bunch of data tables. So number them, get used to that. And what are we going to measure? Well, let's actually put down what we know. So we have the density, let's call it, which is the density of the fluid, which is water, which equals 1 gram per centimeter cubed. I remember that from my chemistry days. Might not be in the units that I want, but that's going to be okay. And then we're lab partners, I go and I half fill the graduated cylinder with water, tap water, and then I drop in the dowel. And what I notice, I'm going to draw a little diagram here, what I notice, to be honest, is that if I look at the dowel, the meniscus kind of sometimes does that. It leans over to one side, and so due to the capillary effect, you get a slightly higher reading on one side. You get a slightly higher meniscus on one side than on the other. What do? I do my best. I mean, I basically do my best to get a reading of it. So, L1, and this is length of dowel or object. And I'm looking back at an old book here, and the length of the dowel is 7.51 centimeters, and my L2, which is the length of displaced water. I know it seems weird, but it's the bit underneath the object, underneath the meniscus to the bottom of the object, and that's going to be 5.7 centimeters. I'm a big believer in writing down what you see, because if you write down what you see, the chances are you will not make a mistake, even though you might want to change the units afterwards. So don't do conversions in your head, because it's a real pain. Do conversions on a piece of paper, if we actually need to convert. So let's be honest about this. I'm looking at a ratio of lengths, so the ratio of L1 to L2 in centimeters is the same as the ratio of L1 to L2 in meters. So although I keep driving into you, you've got to be in SI units. There's times when you're doing ratios, for example, where you don't have to do the conversion. Let's do a calculation. So let's go here and we say calculation. And so what we said was, we said the density of our object was equal to the density of the fluid multiplied by L2 over L1. So in terms of numbers, the density of my object is equal to, and I said 1 gram per cubic centimeter. Let's just leave it in grams per cubic centimeter. And then we have L2, which is 5.7 over 7.51. I'm not actually sure why my group has 2 decimal places for one reading and 1 decimal place and for the other. If they're doing this right, they should be able to put a 0 in there, if you think back about our measurement strategies. So this would be 5.7 divided by 7.51, and this would be equal to 0.7589 something, 759. That would be grams per centimeter cubed. So density, we can say, is equal to, let's just round this a bit, 0.76 grams per centimeter cubed. Okay, so there's my measured value. Now, I'm not going to do it today, but what we could do is we could have said, how small could that value of L2 be? Because that's the one that's got issues. And how big could this value of L2 be? And I could have done a lowest reasonable density of the object and a highest reasonable density of the object. And that would have been, it's always a bit more professional to have a span of values. It just happens that my group at this time, it was a few years ago, so I don't think I made an effort to make them think about that. Maybe I'll do this lab again sometime and do those numbers properly. Okay, so then the next thing is I go to my phone and I look up density of wood, and okay, here we go. Let's go to my phone and then go density of wood, and it comes up wood density chart, and it basically says yeah, it's basically saying the oak, so accepted values. So oak is given as a range of values from, let's have a look, 0.6 to 0.9 grams per centimeter. And let's have a look. This would be American oak, would be 0.74 grams per centimeter cubed. Grams per centimeter cubed. And then we have American white oak, white oak, and that would be 0.77 grams per centimeter cubed. So it's right in the ballpark of oak. Let me just have a the other common woods that are used for this kind of thing are poplar, because it's easy to machine. And let's see if I can get a value for poplar. Yeah, poplar is basically 0.3 to 0.39. Okay, so not likely. So then I come along here to my conclusion. And I say, okay, the measured value of density of the wooden dowel was found to be about, I'm going to say about because I didn't do a range of values, was found to be 0.76 grams per centimeter cubed. This is in good agreement with the typical value of density of oak, O-A-K, oak, and then put in parentheses. You can put down, what do we say, 0.6 to 0.9 grams per centimeter cubed. But there was also American oak would be closer, etc., etc. Clearly wet wood, probably not, or probably more dense than dry wood, etc. It's a lab which is there to show you. The reason why I like this lab is because it looks very hard to begin with. Man, you want to find this density using flotation, and it's just remarkable how the math just, the algebra just cancels things out. And all you have to do is take a ratio of the lengths for a uniform cylinder. Take the ratio of the lengths, and that'll give you the ratio of the densities. It's very nice. Very short lab. It's kind of nice. There we have it.